Hello friends, myself Dr. Nandakumar Aubawale from College of Engineering, Ambazugai is going to deal with Applied Thermodynamics 1. This is 34th lecture. So in previous lecture, we have discussed about supersaturated or metastable flow and numerical on steam flow through nozzle. So yesterday there was a problem in solving one problem. Difficulty with the answers which were not matching to the accurate values. So today we will resolve the problem which we have discussed yesterday, and will simplify it to the more or greater accuracy, and the mistake which was committed in previous lecture we will see what was the major mistake because of which we committed the mistake. So now today we will see the same problem which we have discussed in a previous lecture. So this is a problem. The initial condition of steam to a convergent divergent nozzle. So he says that the nozzle is convergent divergent nozzle. This kind of nozzle is there. So here we have section 1.1, which is inlet, and this is section 2.2, which is outlet or exit, and the minimum cross section, this part is known as cross section is known as throat. Then this is the nozzle where the nozzle is initial condition of steam at the inlet of nozzle is 2.2 meganewton per meter square. So this is pressure P1 at the inlet and 260 degrees Celsius. So temperature of steam at inlet T1 is 260 degrees Celsius. So here pressure and temperature is given, that gives us hint that the steam at the inlet is superheated steam. The steam is superheated steam at the inlet. Then when steam comes out of this nozzle, the pressure of steam falls to 0.4 meganewton. So P2 is 0.4 meganewton per meter square, assuming the frictionless flow up to the throat. So here from 1 to T up to this there is no friction, and beyond this throat there is a friction between steam and nozzle. Then he is saying that the efficiency of this nozzle is 85%. Determine flow rate for throat area of 32.2 centimeter square. So area at throat 80 is given in centimeter square, and also determine exit area, that is area at exit 2 A2. So these two things are given. So these two things are asked. Now let us see. The pressure at the inlet is 2.2 meganewton per meter square. So we have to convert it into bar, that is 22 bar. And temperature of steam at inlet is 260 degrees Celsius, which is superheated steam. And temperature of steam at exit is 0.4 meganewton per meter square. And if we convert it into bar, it will be 4 bar. Efficiency of nozzle which is given is 85%, and the area at throat is given as 32.2 centimeter square. So now here the pressure ratio, pressure at throat divided by pressure at inlet, is equal to 0.546. So this is derived by us in our derivation itself. So here this is the ratio for superheated steam. So already we have discussed it. So this is the critical pressure ratio for the steam, 0.546. Then he is asking us to find out mass of steam and area at exit. So now to find out mass of steam, so mass of steam continuity equation, say for example, if there is one nozzle and if steam passes through this nozzle, so at inlet steam passes at inlet and steam comes out at exit at 2. So the mass of steam which is entering at inlet, m in, is equal to m out. So whatever the mass of steam enters into this nozzle in kg per second, same mass of steam comes out of this nozzle. So this is called as a continuity equation in terms of mass. So here the mass flow rate at inlet is given by A1 V1 divided by small v1, where capital V1 is velocity, small v1 is specific volume. So that is equal to AT Vt divided by small vt, and that is equal to A2 V2 divided by small v2. So here to find out mass flow rate, so already area at throat is given. If we find out velocity at throat and specific volume at throat, mass flow rate through this nozzle can be obtained. So here to know this, first we know area at throat. So velocity at throat can be obtained by using this equation, square root of 2 h1 minus ht into 10 to the power of 3 square root. So here h1 can be obtained because we know pressure and temperature of steam at inlet. P1 is known, T1 is known. We can find out enthalpy of superheated steam. So then afterwards we want to find out HT, enthalpy of steam at throat. So enthalpy of steam at throat can be obtained if we know pressure at throat. So pressure at throat can be obtained by using this correlation, PT divided by P1 is equal to 0.546. So from this we can get pressure at throat. Once we know pressure at throat, so here say for example steam entering is having condition P1 is equal to 2.2 meganewton per meter square, means 22 bar and 260 degrees Celsius. So this is the condition of steam at the inlet. When it comes at throat, so from inlet to throat there is no friction, means the expansion is isentropic expansion. So now enthalpy at throat can be obtained. So how to obtain enthalpy at throat? So to know enthalpy at throat, we must know condition of steam. So condition of steam has to be determined, and from that we have to find out enthalpy at throat. So enthalpy at inlet can be obtained. So condition of steam we know, superheated steam. So to find out enthalpy of superheated steam, we can use this formula, H1 is equal to HF1 plus HFG1 CPS into T sup 1 minus T saturation 1. So this data has to be taken at pressure P1 is equal to 22 bar, and then we know this expansion from 1 to T up to throat, 1 to T is isentropic expansion. So S1 is equal to ST. So entropy at inlet is equal to entropy at throat, because this process 1 to T is isentropic process which is represented by a vertical line. So S1 can be obtained, entropy at inlet can be obtained. So entropy of superheated steam at inlet, S1 is equal to SF1 plus SFG1 CPS T sup 1 divided by TS1 at pressure P1. So once we know S1, so ST can be obtained. So this ST can be obtained assuming that first, if we assume that steam is wet or superheated, so that depends on the the entropy of dry saturated steam at throat pressure, that we will discuss while solving this problem. So here if we get this steam as a wet steam at the throat, then we have to calculate xt, dryness fraction at throat. But if steam is superheated, then we have to find out temperature of superheated steam. So at present in this diagram it is shown that steam is superheated, so which is above this curve. That means if this point T is above this point, then we say steam is superheated. If this point T is inside this curve, then we will say steam is wet. So presently he is saying that steam is superheated. This is the assumption in this diagram. So that we will see whether steam is superheated or wet. Then from that we can find out quality of steam. Then we can find out enthalpy of steam HT at throat. So by substituting HT and H1 in this above equation, we will get velocity of steam at throat. So say we can call this as equation number 3, equation number 1, equation number 2, and this we call as equation number 3. This is equation number 4, equation number 5, equation number 6, equation number 7, equation number 8. So from this equation number 8 and equation number 5, we get enthalpies. We substitute in equation number 3, we will get velocity of steam at throat. Then after getting velocity at throat, so area is known, velocity at throat is known, then specific volume at throat. If steam is wet, then specific volume of wet steam is given by xt into Vg at throat. So we know this dryness fraction xt, and by knowing dryness fraction we can find out specific volume at throat. Once we know specific volume at throat, then we can find out mass flow rate. So mass flow rate of steam can be known. Then we can find out velocity at exit. V2 is equal to 2 into nozzle efficiency H1 minus H2 dash. H2 dash means enthalpy at 2 dash. So this enthalpy we have to find out. Again, to find out H2 dash, we have to find out X2 dash dryness fraction, equating entropy at inlet 1 to entropy at S2 dash. So again we have to find out S1 is equal to S2 dash. So here we will get the dryness fraction X2 dash. So by knowing X2 dash we can find out H2 dash using similar formula. HT is equal to HFT plus XT HFGT at 2 dash. So once we know dryness fraction, we can find out enthalpy at 2 dash, and then substituting it here we can find out velocity at 2. So here by knowing velocity at 2, again he is asking us to find out area at exit. So we will use this correlation A2 V2 divided by V2. So velocity is known, mass is known already by using equation 2, then specific volume at 2 can be obtained. So this specific volume, if we substitute, then we can find out area at exit. So this is the outline of problem, how to simplify this. Now let us see. So before starting, we must know pressures. So first pressure P1 is known, that is pressure P1 is equal to 22 bar. So at pressure 22 bar, we have collected this information from steam table. So saturation temperature 217.2, then Vg 0.09196 meter cube per kg, and so on. So this data is taken at 22 bar. Again we know pressure at exit P2 is equal to 0.4 mega Newton per meter square, that is 4 bar. So at 4 bar we have gathered this information. So there was error, basically error in this information itself. So in previous lecture, while writing this information, so this specific volume was wrong. Again some other values were also wrong. So because of that the error was introduced. That was one of the reason. Now here after that we have to find out pressure at throat. PT divided by P1 is equal to 0.546. That is nothing but PT is equal to 0.546 into pressure P1 is equal to 22, and on simplification we get this as 12 bar. So pressure at throat is 12 bar. So again we have obtained information from steam table at 12 bar. So saturation temperature, specific volume of dry saturated steam, then enthalpy of liquid, then enthalpy of latent heat of vaporization, then the entropy of liquid, entropy of vaporization. We have gathered this information. Now we'll start to solve this problem. So now very first what we have to find out is enthalpy at point 1. So enthalpy at inlet H1 is required. So if we know H1 and HT, we can find out VT, and if we know VT and small vt, specific volume at throat, then we can find out mass flow rate. So our aim is to find out H1, HT and small vt, capital VT, that will give us a mass flow rate. So now to find out H1, enthalpy at inlet of nozzle H1 is given by H1 plus HFG1 plus CPS T sub 1 minus PS1. So HF1 is given here. This is pressure P1, this is pressure PT, and this is pressure P2. So HF1 means enthalpy at point 1 is 930.9, 930.9 at pressure of 22 bar. So here 930.9, 930.9 plus of HFG1. HFG1 at 22 bar is 1868.1, 1868.1, 1868.1 plus of CPS, specific heat of steam, is 2.1 into temperature of superheated steam T sub 1, which is given in the problem as 260 degrees Celsius. So this small t indicates temperature in degree Celsius, 260 degrees Celsius, which is given in the problem itself. T1 is equal to 260 degrees Celsius. Steam is superheated, that's why we call this as T sub 1. So T sub 1 is 260, then TS1, saturation temperature of steam at pressure P1 is equal to 22 bar is 217.2 degrees Celsius, 217.2 degrees Celsius. On simplification, we get this as 2888.8 kilojoules per kg. So this is enthalpy H1. Then after that, to find out entropy at throat, first we must know entropy at inlet. S1 is equal to ST we have to do. So therefore entropy at inlet of nozzle is S1 is equal to SF1 plus SFG1 plus CPS natural log T sub 1 divided by PS1. So entropy at 1 means pressure 22 bar. SF1 is taken from steam table as 2.490. SF1 is 2.490. 2.490 plus SFG1. SFG1 is 3.809. SFG1 at pressure 1. So 3.809. 3.809 plus specific heat is 2.1 into natural log T sub 1. Temperature of superheated steam is 260 degrees Celsius, but here we want it in degree Kelvin. So that's why this is 273 plus 273 divided by temperature of saturated steam is 217 degrees Celsius, 217.2 plus of 273. So on simplification, entropy at point 1 is 6.474 kilojoules per kg Kelvin. So this was same as we have discussed in previous class. So now what we have to do is we want to find out the quality of steam at throat. So whether at this throat steam is superheated, this point T comes here, or it comes below this line, or it comes on this line. So to know this, we have to compare this with the entropy of dry saturated steam at throat pressure. Entropy of dry saturated steam at throat pressure. The entropy of dry saturated stream Hg is nothing but SF plus SFG. So if this entropy which we have obtained S1, if it is greater than this entropy of dry saturated steam, that indicates steam is superheated at the throat. And if this is less than this, this S1 is less than Sg, that indicates the quality of steam at throat is wet. So SF at throat pressure PT, which is 12 bar, SF value at throat pressure is 202.216. So this is 2.216 plus of SFG1 is 4.306. So this works out to be 6.522 kilojoules per kg Kelvin. So now if we see this on Muller chart, so this is the dry saturation curve. So here point 1 we have, and this is point 2. So this entropy which we have obtained is 6.522. 6.522 we have obtained. So this entropy Sg is equal to 6.522, which is greater. So which is greater means this point will be somewhere here. So this dry saturation point will be somewhere here. So which is not below this. So curve is going like this. That means if we take it straight forward, then entropy is less. So entropy is less in the sense this point is not above this, it is below this curve, and it is wet steam. So we'll again we have one more criteria to know this whether steam is wet or dry saturated. So at present Sg at PT is greater than S1. Therefore steam is wet at throat. Steam is wet at throat. Yesterday because of wrong data, so this value was wrong. So this was a bit less than this. So therefore it was highlighted that the steam was superheated. So this data was wrongly taken. Therefore this value was wrong, and because of that we obtained temperature of superheated steam. So now it is concluded that steam is wet at throat. So now if steam is wet at throat, we can find out dryness fraction of steam at throat. So to find out dryness fraction, of steam at throat, so we can equate entropy at 1 is equal to entropy at throat. So entropy at point 1 S1 we have already calculated. Entropy at throat can be written as SFT plus of SFG T into XT. So what is our assumption? Steam is wet. Therefore we have taken multiplication of dryness fraction. So S1 value is calculated as 6.474, which already we have calculated. S1 is equal to 6.474. So this value we have substituted there is equal to SFT. So at throat pressure entropy is 2.216. So 2.216 plus of xt as it is into SFGT. SFGT at throat pressure is 4.306. 4.306. So on simplification, we get this dryness fraction xt is equal to 0.988. So if this xt is equal to 1, then we can assume that steam is dry saturated. If this xt, if we get greater than 1, if xt is greater than 1, so that indicates steam is superheated. So here, as xt is less than 1, as xt is less than 1, our assumption that steam is wet is correct. Why it is correct? Because this dryness fraction which we have obtained is less than 1. So therefore this assumption is correct. If this dryness fraction is greater than 1, then we have to do some other exercise. So S1 is equal to ST we are going to write. So S1 is equal to, so this steam is superheated. That indicates if xt is greater than 1, then steam is superheated. So this formula will change. So this formula we have to change. So which formula we have to write? So that is nothing but SFT plus of SFGT plus of CPS natural log T sup T divided by T saturation at throat. So from this SFT, SFGT, CPS and T saturation T, we can get from steam table only unknown is T sup T. So temperature of superheated steam at throat can be obtained. So that yesterday we did. So right now this is not required here because steam is wet. Our assumption is correct. Therefore, whatever formula we have used here is correct, and from that we obtain dryness fraction at throat. Now, enthalpy of steam at throat. Enthalpy of steam at throat, that is HT, is given by SFT plus of XT into SFG at throat. ST at throat is already known, that is, sorry, this is wrong, HFT. We are finding enthalpy HFT and HFGT. So this formula HT we are finding enthalpy, therefore HFT plus of XT HFGT. So at throat, enthalpy at throat pressure can be taken from this table as 798.4. Is 798.4. 798.4 plus of XT is 0.988 into HFGT. HFGT is 1986.1. 1986.1. So at throat pressure, HFGT is 1986.1. So 1986.1. So HT, enthalpy at throat, can be obtained as 2762.36 kilojoules per kg. So now we know enthalpy at throat. So once we know enthalpy at throat, so velocity at throat, velocity of steam at throat, V2 is given as V2 is equal to square root of V2 is equal to square root of, sorry, Vt, velocity at throttle, Vt is equal to 2 into h1 minus of ht into 10 to the power of 3. And nozzle efficiency, if we write here nozzle efficiency, top to throttle, nozzle efficiency is 100% because he is saying that there is no friction between inlet to throttle. So this is 100% in the sense it is 1. So this value nozzle efficiency is not required. So again here we can write this as square root of 2 into h1 value we know, which we have calculated it as 2888.8, 2888.8. So this is 2888.8 minus of ht is 2762.36 closes bracket into 10 to the power of 3. So on simplification we get this velocity of steam at throttle is 502.87 meters per second. So velocity of steam at throttle Vt is equal to 502.87. So now what is our aim? Aim is to find out mass flow rate. Mass m is equal to area at throttle into velocity at throttle divided by specific volume at throttle. So we know area at throttle, which is given in the problem, velocity just now we have calculated, specific volume of steam at throttle has to be calculated. So specific volume of steam at throttle Vt is given as xt into Vgt. So xt is dryness fraction and Vg is specific volume of dry saturated steam at throttle. So dryness fraction of steam at throttle, which we have calculated as 0.988. So this is 0.988 into Vgt, specific volume at throttle pressure. So specific volume at throttle pressure is given as 0.1633. 0.1633. This is the value of specific volume at throttle pressure. So this is 0.1663. 0.1633. On simplification, this specific volume is 0.16. So it was wrong in yesterday's lecture. Yesterday we had committed mistake here. So meter cube per kg is the specific volume. So this was wrong. So therefore answer was going wrong. So mass flow rate m is equal to area at throttle into velocity at throttle divided by specific volume at throttle. So area at throttle is 32 point, I think 2. Area at throttle is 32.2 centimeter square. So 32.2 centimeter square into 10 to the power of minus 4, because we want to convert this into meter, dividing it by 100 square. 100 square means 10 to the power of minus 4 into velocity at throttle. Just now we have obtained as 502.87. 502.87 is the velocity at throttle. 502.87 meters per second. This was meters per second divided by specific volume at throttle is 0.16. So mass flow rate after simplification we get as 10.12 kg per second. So this is the mass flow rate. Now we are supposed to find out velocity at exit. So one answer we obtained, mass flow rate of steam is 10.12 kg per second. Now we want to find out velocity at the exit. So velocity at exit is given by velocity at exit, velocity of steam at exit V2 is given by square root of 2 into h1 minus h2 dash into 10 to the power of 3 into nozzle efficiency. Now here what we know, h1 is known, nozzle efficiency is known, h2 dash we have to find out. So how to find out h2 dash is important. So here on Molière chart if we see, so this is 0.1, this is 0.2, sorry 2 dash, and this stream expands like this up to 0.2. So this is pressure at exit P2, this is pressure at inlet P1, and here pressure at torsion P2. So now H1 is known already at 0.1, this is throat, and this is 0.2. So H2 dash is nothing but entropy at 0.2 dash. So to find out entropy at 0.2 dash, we must equate entropy at 0.1 is equal to entropy at 0.2 dash. Entropy at 0.1 we have calculated S1. Entropy at 0.2 dash can be known. So from here we can find out dryness fraction. Once we know dryness fraction at 0.2 dash, then we can find out H2 dash. So here SF2 dash plus of X2 dash into SFG2 dash. So this is the equation for finding entropy of wet steam. Already S1 is known. S1 value is 6.474, which we have calculated already. So S1 value is calculated here as 6.474 kilojoules per kg. So that value we have substituted. SF2 dash. SF2 dash. So entropy at 2 dash. Pressure P2. The SF2 dash is 1.776. 1.776. 1.776 plus of X2 dash, which we want to find out, into SFG2 dash. SFG2 dash can be taken from steam table as 5.118. So SFG2 at pressure 2, 5.118, 5.118. So from this we get dryness fraction at 0.2 dash, X2 dash as 0.91, 917. So this is dryness fraction at 0.2 dash. So from this we can find out enthalpy at 2 dash. Enthalpy at 2 dash is nothing but H2 dash, which is equal to HF2 dash plus of X2 dash into HFG2 dash. HF2 dash is 604.7, 604.7, 604.7 plus X2 dash is 0.917 into HFG2 dash. HFG at pressure 2. HFG at pressure 2 is 2132.9. 2132.9. 2132.9. 9. So here we get this enthalpy as 2562.56 kilojoules per kg. So this is enthalpy at 2 dash. So once we know enthalpy at 2 dash, we can find out velocity at 2, V2. So V2 is equal to, already we have written equation, V2 is equal to 2 into nozzle efficiency into h1 minus h2 dash into 10 to the power of 3. So here square root of 2 into nozzle efficiency, which is given as 0.85 in the problem, 0.85 already it is given, into h1 value is already, which we have calculated as 2888.8, minus of h2 dash is 2562.56, which just now we have calculated, into 10 to the power of 3. So on simplification we get velocity as v is equal to 744.8 meters per second. So velocity v2 is known. Now why we are going to find out velocity at exit? So he has not asked us to find out velocity at velocity at exit. He has asked us to find out area at exit. So we know one equation, m is equal to a2 v2 divided by v2. So mass already we have calculated as 10.12 kg. Area at throat is asked. So area at exit is asked. So velocity we have obtained. Now if we know specific volume at exit, then if we substitute everything we can find out area at throat. So our aim is to find out v2. So v2 is equal to x2 into vg2. So here x2 is obtained, and that is x2 dash is obtained. So x2 dash and x2 are very much close to each other, therefore we assume actually this is not going to be same. So x2 is greater than x2 dash, so it is little bit greater but approximately same. So here x2 is 0.91 into vg2, so it is approximately same, assuming that x2 dash is equal to x2. Okay, then vg2 specific volume at exit pressure is seen from the steam table which is at pressure 2 specific volume is 0.462, 0.462, 0.462. So v2 we get as v2 as 0.42, 0.42 meter cube per kg. Once we know v2 specific volume v2, so what we know in this equation, capital V2 we know, small v2 we know, mass we know, only area at exit is not known. So we will write here mass is equal to area at exit into velocity at exit divided by specific volume at exit. So here we want to find out area at exit. A2 is equal to m into v2 divided by capital V2. Mass flow rate is 10.12, which we have calculated here. You can see here mass is equal to 10.12 kg per second into specific volume, just we have calculated as 0.42 divided by velocity is 744.8. This we have calculated. Velocity at exit is 744.8, 744.8 meters per second. Now in simplification we get this as 5.706 into 10 to the power of minus 3 meters square, or else we can write this as 0.005706 meters square, or if we want to convert it into centimeter square, multiplying it by 10 to the power of 4, so this will be 57.06 centimeter square. This is area at exit. So this problem is a solved problem in the book, but he has used the Molière chart to find out the values of enthalpy, everything. So if we see here in this, so this is H1. So we obtained H1 as 2888.8. So this is the difference. Okay, then HT, enthalpy at throat, we obtained as 2762.36. 2762.36. So this is 2790. Then H2 dash, which we obtained is H2 dash 2562.56. 2562. So this value is here 2562.2590. So these values which we have obtained are by analytical method, but in book he has used graphical method. So there is an error. Already I have explained you, there will be error between analytical method and graphical method. So more error difference will be there between graphical and analytical method. Graphical method is having more errors compared to the analytical method. So answers are going to be different. So this is how we obtain this area. So final answer is mass flow rate M is equal to 10.12 kg per second, and area at exit A2 is equal to 57.06 centimeter square, because while giving area at throat he has given in centimeter square, therefore this area at exit we have to give in terms of centimeter square. So this is how the mistake which was committed in yesterday's lecture is rectified.